What's up, everybody? Hope you're doing just fine. Today we're excited to announce to you that we'll be starting our full stack practical deep learning course featuring TensorFlow, HuggingFace, weights and biases, and KubeFlow. Don't forget to subscribe and hit that notification button so you don't miss any part of this series. Artificial intelligence is everywhere, be it in optical character recognition systems like this, which help automatically extract information from files, in object detection systems where the machine is able to understand its environment, in visual inspection systems, like in this case where Landing AI is using this artificial intelligence tool to detect defects in electronic equipment. We also have this in the health sector where we detect certain diseases in the human breast. We have applications in image captioning, self-driving cars, voice transcriptions, and question answering, just to name a few. Before taking a look at these different tools we'll be using throughout this course, let's start with an introduction to deep learning. Deep learning is part of this vast computer science domain known as artificial intelligence. Artificial intelligence itself involves teaching computers or machines do tasks which are usually done by humans. In classical artificial intelligence or AI algorithms, we feed the computer with a set of rules such that when given the inputs, the machine is able to produce some output. So supposing we want to build an AI algorithm which teaches a computer how to play the game of chess. In that case, you'd pass in a set of well-defined rules such that the machine learns how to play the game of chess based on the rules you've given it. Now, in other subfields of artificial intelligence like machine learning, the way the machine learns is quite different. In this case, what we have is a machine learning model which has been given initially the inputs and the outputs. So the machine initially gets both the inputs and the outputs. And usually we're dealing with a pretty large number of input-output pairs. Once the machine is done learning from these training examples, which make up what we call the training set, the machine is now fed with new input which it hasn't ever seen. Based on just this input, the model is now able to predict a new output. Let's look at this simple example. Here we're having this Detectron tool car damage detection notebook from Kaggle, in which we have this data set which can permit us train a model such that it learns how to correctly say whether a car has been damaged or not. In some cases, we may be able to say exactly at what point or in what region is the damage. So looking at this car here, we see clearly that it's a damaged car. We could click on this other one, see we have this damage, we have this damage, and so on and so forth. Before going any further, let's understand how these machine learning models are built such that they could learn from data. Firstly, we suppose we have this input data, that's this input image right here, and then we have an output which is taking a value of say 1. Now this value could be 0 in the case where this image isn't that of a damaged car. So if it's an undamaged car, we have the value 0. In this case, it is 1. So we have this, our output y would take this value 1. Now, our system takes in this image, it does some pre-processing, and then we have our input x. This is the input which gets into the model. Now, machine learning models could serve in several domains, and so this pre-processing unit right here is highly dependent on the domain in which we're working on. So if we're working in NLP, that's natural language processing, and we have, for example, input which is text, we would have this pre-processing unit built such that we are able to convert that text into information that the model will understand. In this case, we are having this input image, which itself is made of pixels, which each take values ranging from 0 to 255. For now, we will not get into how this pre-processing unit works. We just understand that we have this pre-processing and we have the input. Now, once we have this input, we get straight into the model right here. So we'll just have this. We'll suppose that here's our model. We're using a very simplified model right here so that anyone could understand regardless of your background. So you don't need to have a math degree to understand what we have to explain right here. And trust me, if you could understand this, then you'll find, because in this course we'll stress more on how to use tools like TensorFlow and HuggingFace to train your machine learning models. So let's look at this. We have this input x, which we've seen already, and then this input is passed into these two functions. We have f of x1 and then we have f of x2. The way f of x1 is gotten from x is that we have in a constant. So let's put in a constant here, a, we have a1, and then right here we have a2. Here let's say we have b1, and here we have b2. So the way we get this f of x1 is simply saying f of x1, that is, we have this f of x1 equals x, this input, times this constant a1, which gives us now f of x1, and then f of x2 is equals x times the constant a2. Now notice how we have for each path its own constant. So here we have f of x1, f of x2. Now how do we get the output y? We repeat the same process. Here we have y equals b1 times f of x1. So we have b1 times f of x1. But notice that to obtain y, we also need to take into consideration this information which is passing in this direction right here. So what we have now is, instead of just having b1 times f of x1, we have b1 times f of x1 plus b2 times f of x2. And if we make use of what we had right here, we see that f of x1 is a1 times x. So we have a1 times x, f of x2 is a2 times x. There we go. We have seen how from this inputs we're able to obtain the outputs. But how does this permit the machine to learn from this inputted data? The way this works is, we have here these constants which are known as weights. So in case you're new to machine learning, you would have to get accustomed to this term as you'll be using it very frequently. So right here we have what we call the weights, which define the way the model will produce an output based on the inputs. So this means that once you pass in an input like this image right here, these weights are modified. So let's suppose that we initialize the weights to a value of say 0.02 right here. A2 equals 0.02 and this 0.02, this 0.02. So we have all these four values initialized at 0.02. Then we would have a certain output right here. But then if we know that we have this input and we have an output of 1, then with our machine learning algorithm, we are able to modify these weights or these parameters right here such that once we get the image, we are able to get the corresponding output which matches exactly what we expect. That said, after training our model, instead of having a value of say 0.02 here, we may have a value of say 0, and here we may have a value of say 0.3, here we may have 0.4, and then maybe here we will have a value of 0.02. Now note that this is a very simplified model, and this is not the kind of models we use in practice to learn from this kind of input data like images, as we could see here. But nonetheless, the principles still remain the same. So coming back to our model, we've seen that we have this input to the model, we have this intermediary values here which we'll call neurons, we have this constants which are modified during the training process such that their values permit us get certain outputs based on the inputs. So here we have our weights A1, A2, B1, B2. Now in machine learning today and deep learning, we're used to having models which are over even up to 1 billion parameters. So you hear that this model or that other model has 1 billion parameters, and that simply means we have 1 billion of these types of constants. So this is to tell you of how complex the models we deal with today have become. We could complexify this model by having this even more complex, or better said, deeper model. By deeper here will simply mean that we have stacked many more layers. Now note that here we had the weights, we had this neurons, and then we have the layer. So understand that a layer is simply these nodes or neurons right here which have a common input and a common output. And the way this layer or the way this neurons in the layer interact with the input in order to produce the outputs is dependent on the type of layer we're working with. Sometimes we may have dense layers, or what we call linear layers. That's practically what we just saw right now. That's where we had to take the input, multiply by some weight, and then get the output. So those are dense layers. And then we could also have convolutional layers. We'll see this subsequently. We could have recurrent layers. We could also have transformers and a host of many other different layers which we could create. So we could have here transformers. Now note that these are the most common which are used in practice. That's in deep learning practice. Now we just mentioned the term deep learning. It's in fact a branch of machine learning, but one in which specializes with models which have many layers which is stacked between the inputs and the outputs. Hence the term deep learning. Also note that this kind of machine learning model is known as a neural network. You now understand that deep learning is part of machine learning, which itself is part of artificial intelligence. Let's look at this categorization of machine learning algorithms. We have supervised learning, unsupervised learning, and reinforcement learning. In supervised learning, what we have is very similar to what we've seen already, where we have a model which has been trained with input-output pairs. Whereas with unsupervised learning, we don't have this outputs during training. So we just pass in the inputs and the model learns from these inputs. This turns out to be very interesting in cases where getting the outputs is quite tedious. Let's take this simple example. Supposing we have this input right here, that's an input speech. Let's have this input speech, and then we have this model which takes in this input speech and then transcribes it. So supposing we say hello and then we transcribe this, we have hello. We could build a model as a model like this, which does this transcription automatically. And to build this kind of model, we need the inputs and the outputs. Hence, this is a supervised learning problem. But then, if we're able to come up with a model which doesn't need these transcriptions, then all we'll be doing is simply passing in this input voice, and then the model automatically learns how to extract this vocal information automatically. In that case, we're having an unsupervised learning problem. We see that if we were to train a model using the supervised learning technique, and we're working with say 100k input audio sounds, we will need 100k different transcriptions. Whereas in the case of unsupervised learning, we could simply gather this voice data without bothering ourselves on how or where we're gonna get the transcriptions from. This permits us not only easily train such models, but also help in expanding, or better still, democratizing the use of such machine learning models, as now someone in some village in India could just produce training data in their local language very easily, since now we do not need the outputs, that's the transcriptions, anymore. So all we need to do is just pass in the inputs and the model learns from these inputs. The other type of machine learning is reinforcement learning. To understand reinforcement learning, we are going to consider an environment, an interpreter, and an agent. The interpreter gets information about the environment and then passes it on to the agent. And then the interpreter rewards the agent depending on how well it took this action. And so at the end, we have this agent which is learning how to take the best actions since it's been rewarded by the interpreter. A simple application of this could be in the chess game. So our environment is a chess board, and then we are trying to train this agent to make the best moves based on the current state of the environment, and also using the reward system from the interpreter. One of the main reasons why machine learning and deep learning today have become very popular is thanks to the fact that we have huge amounts of data available today. And it also turns out that as we increase the training data, that is the data we use in helping our models better understand the environment, there is an increase in performance when it comes to deep learning algorithms. So where the classical machine learning algorithms start plateauing, the deep learning algorithms keep performing even better. That said, today we have specialized hardware like the GPUs and TPUs, which permit us train these models way faster than what we would have done about 20 years ago. Finally, we also have machine learning algorithms, which are state-of-art methods in several domains like computer vision and natural language processing. So as we get into this course, one of the most important points to note is that the machine learning model can't do much without proper data. So make sure you treat your data very well. By treating your data very well, we simply mean gathering as much useful and cleaned data as possible. To elaborate on that point concerning the useful data, let's consider that you've trained a model which is able to take as input this kind of image and then correctly says that this is a damaged car. Now, supposing all these images were captured at daytime and that you now have to do predictions, or the model has to do predictions in nighttime. But because the model has been taught how to predict an input image to contain a damaged car by using images or inputs from daytime, this model may not perform very well. From the moment you start building machine learning models and training them, you may be tempted to think that a machine learning project is all about just building a model and then training it. That's why we said previously that you have to be very careful about the way you deal with your data. That said, let's look at our proposed machine learning development life cycle. When building a machine learning product, we'll want to start with a task. Like in this case, where we want to detect damaged cars, our task will be that of taking in as input an image and predicting whether that image contains a damaged car or not. Then we'll move on to data. In the stage of data, we may make use of readily available data on the internet, or as in most cases, we would have to gather our own data by ourselves. Now, imagine building a model based off a certain type of car and then wanting to test that same model on a completely different set of cars or completely different type of cars. That obviously wouldn't be a great idea. So upfront, we have to make sure we gather useful and representative data. In the next step, we'll go straight into the modeling, that is coming up with some machine learning or deep learning model which will permit us extract useful information from the inputs. In this case, where we're wanting to extract this information on whether the car is damaged or not, we would use typically convolutional neural networks. We'll be looking at this shortly, so don't bother if you don't understand that. From this, we'll go straight into error sanctioning. In error sanctioning, basically what we're doing is we're telling the model that in this example, as we have here, we know that we have this image and that the output is meant to be a 1, saying that it's a damaged car. So If our model readjusts its weights such that the output we have here is a 0, then we are going to penalize the model for producing a wrong output since we know the right output. And so this is the process of error sanctioning, which is part of our training process. But before getting to training, we have to define our error function or our loss function. From this, we'll go straight into training and optimization using the gradient descent algorithm or a variant of the gradient descent algorithm. We'll look at this shortly. And then from there, we have to evaluate our model. So it doesn't suffice just to train the model. We also have to evaluate this model. From evaluation, validation, we get into testing the model, that is actually seeing whether this model works. And from there, based on this performances, we are able to come up with some corrective measures. So take note that we don't just build and then finally test, but we also have this feedback where based on what we see or based on the performance of our model, we are able to come up with some corrective measures at the different stages of our pipeline. So we have, for example, the data, so we could modify the data. If in case our model isn't performing very well, we could go ahead and gather much data or much more representative, useful and cleaned data. We could go ahead and modify the model, modify the error function, modify the training process, modify the hyperparameters. We're going to look at this shortly and ensure that we get the best out of our model. But as we said right from the beginning, you shouldn't get scared, as in this course we'll be using tools like TensorFlow, HuggingFace, weights and biases, and KubeFlow to help us in our machine learning development life cycle. Apart from these algorithms, we have amazing tools which permit developers all around the world come up with deep learning and machine learning algorithms very quickly. Before the days of tools like TensorFlow and PyTorch, developers had to write their own machine learning algorithms all from scratch. But today, that's no longer the case, as we have a fully fledged TensorFlow ecosystem consisting of different components which permit anybody load and pre-process data for training these models, building, training, reusing, and evaluating the models, and then deploying these models. This deployment can be done on different platforms like the cloud, like mobile platforms, the web, and many other edge hardware devices. Apart from deep learning libraries like TensorFlow, PyTorch, or Fast.ai, we also have domain-focused products like HuggingFace, where we have thousands of free models which we could use seamlessly in our NLP projects. We have, for example, this DistillBird model which we could get on the go, model description, how the model is used. Notice the few lines of code you actually need to get started with this kind of state-of-art NLP models. So here we go, and then we could actually test this. So the goal of life is mask. So this is a model which fills up with this mask. We'll run compute. So we have here the highest probability. The goal of life is happiness, and you bear with me that this answer is quite great. Let's modify this input and say, for example, so let's go ahead and modify this. We have same time last year. I felt the, and I'll put that as mask. So same time last year, I felt the dash to go skiing. Run that, and that's it. So you have this urge. I felt a need, a temptation, desire, compulsion. So This model works very well in this set task, and it could be added into your TensorFlow or PyTorch code base very easily. Now, when running machine learning experiments, it may happen that for even the same problem, you run the experiment like say 100 times, and then you want to track those models which perform the best. Apart from tracking the model, you may also want to version even the data you're using to train these models. Weights and biases is one tool which comes very handy in helping you manage your machine learning projects. This is trusted by over 100,000 machine learning practitioners, could integrate very quickly in the common machine learning libraries. As you can see here, TensorFlow, PyTorch, Keras, Scikit, HuggingFace, XGBoost. And so they help you manage your machine learning projects while working or without changing much on your initial code. We also have this right here, visualizations. So you see, we're going to look at this shortly, but we could have this type of hyperparameter tuning visualizations and even the model prediction visualizations. Lastly, we could collaborate in real time. So if you're on a team and we want to discuss the current state of a machine learning project, weights and biases is the right tool. The last but not the least tool we'll be looking at in the series is KubeFlow, which will permit us deploy automated machine learning workflows known as pipelines in a portable and scalable manner. You will get to experiment with workflows locally on Jupyter notebooks and then deploy them when you're ready to the cloud. You also have a custom TensorFlow training job operator readily available with KubeFlow. You could easily serve models, build pipelines, use several other frameworks, and leverage this open and welcoming community. Throughout this course, we'll be adopting a code-first approach, and the environment we'll be using is Google Collab. You could just type in right here Google Collab. We have right here collab.research.google.com. Google Collaboratory or Collab permits us write and execute Python in our browser with zero configuration required, free access to GPUs, and easy sharing of our projects. Now, this is very similar to our Jupyter notebook in the sense that right here we have some text and then we have a code cell which we just run by clicking on this or pressing Shift Enter. So that's it. We just have this. Let's run this, for example. You see, seconds in a day equals 24 by 60 by 60, and after running this we should get a simple response. Here's our response. Another good news is we wouldn't need to install TensorFlow, so most of our packages will come already installed and we just have to use them. Throughout this course, we'll do our best to explain each and every concept while maintaining our code-first approach. So if you want a course in which you would get the math behind every concept, then you can get to this course, Deep Learning with TensorFlow 2 on our platform, where you'll get this kinds of theoretical explanations coupled with practice. But for this course, we'll focus on the code. Thank you for getting up to this point, and see you next time.